All right, so we're going to start off this week by looking at section 7.2. In 7.2, we're going to be looking at inverse trig functions. And we're going to focus a lot on like the domain and the range and what the picture of them looks like. Okay, we've already done a little bit with inverse trig in terms of like solving an equation if you had something like this. And we talked about how we solve that by taking the inverse sign of what's on each side. Today, that's not as much the focus. Really, we're going to focus more on domain, range, and what they look like. All right. So first, let's talk a little bit about what an inverse is in general. Okay. An inverse trig function, or any inverse function, is a mirror image, okay, of the regular function. So a regular function and its inverse are mirror images. But they're not mirror images over an axis. Okay? They are mirror images over the line y equals x. Okay, so let me show you that on the calculator. So to show you what that looks like, I'm not going to graph a trig function. I'm just going to graph functions that are more familiar from algebra. And I'm going to start with the squaring function. So I'm going to graph x squared. What function is the inverse of squaring? We don't call this inverse squaring. There's a name for it.
Square root.
Square root. Yeah. In inverse trig, we do call the inverse function inverse sine. But when we're talking about like squaring, the inverse is called a square root. Okay, so I'm going to graph those two. I'm just going to focus on quadrant 1. And I'm going to go from 0 to 10 on the x and the y. Okay. All right, so there's x squared. And there is the square root. And they're not reflections over the x or the y-axis, but they are reflections over the line y equals x. Okay, so if I put that line in, and you look at it, if you were to fold that right on the black line, the blue graph would land directly on top of the red graph. Okay. Any questions on how those two functions are mirror images over that black line? All right, and that's specifically for squaring and square rooting, but that's true for any two functions that are inverses. If you draw that black line, they will be mirror images. Okay. All right, so now, for a function to have an inverse, and I'm going to add something to that. That's also a function. So if you have a graph that's a function and you want it to see if its inverse is a function, it has to pass the horizontal line test. Okay, the horizontal line test is very similar to the vertical line test. Basically, if you can draw a horizontal line and it only hits your graph once, it passes the test. Right? If it hits it more than once, it fails the test. Okay? And what the horizontal line test tells you is if you have a graph and you draw a horizontal line, it tells you if the inverse of that graph is a function. Okay? The vertical line test tells you if the graph you're looking at itself is a function. Okay? Why don't you hang on so that way I can check it at the same time because I don't want to forget. So you can, if you want to show me like at the end of class, if you want to come back up, we can check it off. Yeah. Thank you. So the horizontal line test tells you if the inverse of your graph is a function. Okay, let's look at sine. Okay, this is what sine looks like. I just drew a couple cycles. If I put a horizontal line like that, move the line up, does the horizontal line hit the graph of sine more than once? Right. So that means it fails the horizontal line test. Because the graph of regular sine fails the horizontal line test, that technically means that its inverse is not a function. Okay? But that's an issue. Okay? We need the inverse to be a function. If it's not a function, then what's going to happen when we do inverse trig is that we're going to get an infinite amount of answers to a problem. Okay? And we don't want that. Right? We want to see if we can narrow this down so when we do inverse trig, we get one answer to the question. So we need to make it somehow so this graph passes the horizontal line test. It cannot fail it. Right? So anybody have an idea of what we could do to make that graph pass the horizontal line test? Yeah?
Compress it?
What do you mean compress? Well, we want to keep it looking exactly the same. So we don't want to stretch or compress it at all. But what could we consider instead of the whole graph? What could we do? Yeah?
Got a simple cycle?
Yeah, we could find a section that passes, right? So if we can find a section of this graph that does pass the horizontal line test, then we can use that section alone to make the inverse, right? And that's okay. So maybe the entire graph we can't find an inverse for, but one section of it we could. So the solution to that problem is we're going to restrict the domain of the original function. And leave another line or so below that because we have to figure out what we're going to restrict the domain to. All right, so let's take a look at this. And what this will basically do is it's going to block out everything except one section that I want to focus on. Okay, I tried to make it, it's a little bit off, but it's about 2 tick marks wide. All right. So let's look at that section right there. Does that section pass the horizontal line test? No. Okay, so let's keep going. Let's slide it a little more this way. Okay, how about that section right there? Yeah. Okay, no matter where you put the horizontal line in that section, it will only hit the graph one time. Okay, I know it starts to look a little flat. It's just because the graph is blocking. But yeah, it only hits it one time. So the key is we got to figure out how far left and right those tick marks are. Okay. So we're going to focus on going from here to here. That's the section we're going to consider when we talk about the inverse. Does anybody remember, if we look at these tick marks right there, how much is each tick mark on that graph worth? Yeah? Each tick mark is pi over 2. So that's 0. That's pi over 2. Pi. 3 pi over 2. 2 pi. And going back this way, that's as far as we need to go. So if we restrict the domain to be between what and what, we have a section that passes the horizontal line test. Between, yeah?
Negative half pi and half pi.
Yeah, it's a negative pi over 2 to pi over 2. It's not the only section. You could use a section over here like that. You could use another section over there like that. But that is the most common section that is used. Okay, negative pi over 2 to pi over 2. Okay, so that's what we're going to restrict the domain of the original to. And the reason we're doing that is to force it to pass the horizontal line test, which then means the inverse of sine will now be a function, which is what we want. All right. So any questions on that part? Okay, so now let's graph inverse sine. Okay, let's see what it looks like. Remember, when we write inverse sine, we usually don't write it out in words. We usually just put the sign with the -1. What's another way you can write inverse sine that I mentioned last week? Anybody remember the other way? Begins with an A. Yeah.
Is it arc sine?
Yep, arc sine. So you could write it that way. I think in this section I'm mostly going to use the negative one. All right, so let's draw this. Let's do, and I am going to do it in, we'll do it in radians. I'm going to type in second inverse sine. Okay, I'm going to do zoom 7. All right, so that's what inverse sine looks like. And first of all, does that look like it's a function? Does that pass the vertical line test? Okay, yeah, and it should, because we know the inverse passes the horizontal. Okay, so the original passes the horizontal, so that means the inverse would pass the vertical. Okay, so it is a function. Let's zoom in a little bit and see if we can figure out how far left and right and how far up and down it's going. Okay, so on the y-axis, my tick marks are going by 1s. Okay, so that's going to make it pretty easy to figure out how high and low it goes. It's going, looks like it goes up to 1 and it goes down to -1. All right, so let's zoom in a little bit on that. Yeah, so it's definitely, looks like it goes a little bit past it, but it, let's see, is each tick mark, actually no, it does. It goes a little bit past it. So we got to actually figure out how much past it it's going. And now, let's look at left and right. Okay, right now we've got -8 to 8. Let's see if we can zoom in a little bit. Let's try like -3 to 3. Okay, so definitely that's still in the window. So that's a pretty good window to see the graph. All right, so let's look at that graph. And let's see if we can figure out how far left and right it's going. It's kind of hard to see what's happening because all of a sudden when you get to the left and the right end, it starts to curve, and it almost looks like it's going vertical. Okay. So let's try going to second. Let's go to our table. And let's keep typing in x values till we get right to the point that looks like it's on the end, the right edge of that graph. Right. So let's try like 0.5. Okay. Let's try 0.8. Okay, we're at 0.92. 0.9. Okay, we can still do that. Let's jump up to like 1.2. No, we can't go that far. Okay, so the graph does not go to 1.2. Right, let's try 1.1. Right, doesn't go that far. Let's try 1.0. Okay, so it goes there. Let's try 1.01. Okay, so it looks like this graph stops at 1. It doesn't go any further to the right than that. And looking at the picture, it's kind of hard to see that. It doesn't look like it's going, because my tick marks, the tick marks on the x-axis do not go by 1s. They're going by like pi over 2s. That's why it's kind of hard to see where that graph stops. Okay. If I make the tick marks go by 1s, I think you'll be able to see a lot easier that it looks like it's going right to 1 and it's going left to -1. Okay. All right, so that is my domain for inverse sine. Let's write that down. How about the range? Okay, we know when we go all the way as far to the right as we can, we're at 1.57. That's this point right here. Does anybody recognize what that number is, 1.57? It's something in terms of pi. Yeah? That is pi over 2. Yep. Pi divided by 2 is 1.57. Okay. Let's check the left edge and see if we can find how far down it goes. So we know it goes right to 1, and the farthest left it goes is -1. And that puts me, -1 puts me at -1.57. So we go as high as 1.57 and as low as -1.57. So then what's my range in terms of pi? From what to what? Yep.
Negative pi over 2 pi over 2.
Negative pi over 2 to pi over 2. That is the domain and the range of inverse sine. Now, I want to think how that connects to what we have in that box right there. That's original sine. Okay, that's the original. Let's write down the domain and the range of the original, just focusing on what's inside that red box. Let's start with the range. Inside that red box, how high and low does the graph go? That's the graph of regular sine. Yeah.
-1 to 1.
Yeah, the range is -1 to 1. Good. And how about the domain? How far left and right do the edges of that box go? We made that box, so we should know what we set the left and the right edge to.
Negative pi over 2 pi over 2.
Yep, that was what we restricted the domain to. Negative pi over 2 to pi over 2. Okay. This is for original. Look at the domain and range that we have for the original sine, and look at the domain and range we have for the inverse. How are they connected? Yeah.
They're flipped around.
Right, they're flipped. Anytime that you look at an original function and its inverse, the domain and the range switch. And that's because of this. That basically says y turns into x, x turns into y. Y is equaling x. They're switching places. Right? That's why the domain and range switch. All right. So I was going to write that here, but I think I already wrote it down over there. So the graph of inverse sine has a domain from -1 to 1 and a range from negative pi over 2 to pi over 2. So if you forget it and you get confused thinking about the inverse, then think back to the original. If you can remember the domain of the original, then you know the range of the inverse. Okay? If you can remember the range on the original, then you know the domain of the inverse. Okay? They just switch. All right. Now, let's do the same thing for inverse cosine. Okay, let me get a blank page here. Let's start by graphing regular cosine. And the goal is to look at that and see if it passes the horizontal line test. Okay, so what do we think? That's the graph of cosine. Does it pass the horizontal line test? No. So now what does that mean? If we consider that entire graph, it doesn't pass the horizontal line test, which means, yeah? Okay, but what if we don't? What would happen?
Infinite solutions.
Okay, which means that its inverse is not a function. Yeah. So right now, if we look at cosine and consider the entire graph, its inverse would not be a function because that fails the horizontal line test. Okay. So let's set up a box and see if we can find a section that does pass. Okay, let's try the same box we did last time. Negative pi over 2 to pi over 2. Okay. if I use that section, does it pass the horizontal line test?
No.
No. So for inverse cosine, the negative pi over 2 to pi over 2 doesn't work. Okay. Let's try sliding the box. Let's push it to the right 1 tick mark. Let's try that right there. Does the section inside the box pass the horizontal line test now?
Yes.
Yeah. Let's write this down. This is the original. Okay. Normally you don't write original cosine. I'm just trying to differentiate it so you know I'm not talking about inverse. Okay. So the original cosine. What can we limit the domain to force it to pass the horizontal line test? Yeah. 0 to pi over 2 would be right where that dotted line is. So where our right edge of the box is past that. Yep.
Pi.
Yep, 0 to pi. If you limit the domain to be from 0 to pi, you will have a section that passes the horizontal line test, which now means the inverse cosine is a function. How about the range? How high and low does cosine go in that box? Yep. Yep, it's -1 to 1. Okay. That's the domain and the range that we're going to use for the original cosine. When we talk about inverse cosine, what's going to happen with these two things? Yep.
They're going to switch.
They're going to switch. So now the range is going to be from 0 to pi. There's your range, 0 to pi. And your domain is going to be from -1 to 1. Domain is from -1 to 1. All right, so now I'll do a quick graph of that so you can see it. Let's do inverse cosine. Okay, domain, I'm going to do -2 to 2 just to have a little bit of extra space on the sides. -2 to 2. And range is 0 to 3.14. I'll just go like -0.5 to 3.5. Okay, gives me a little extra. So the graph of inverse cosine should fit perfectly in that window. And again, I have a little bit extra. That's inverse cosine. Any question how we came up with the domain and range for that one? Okay, and most of the time, I really don't memorize that. I just think of the original. I picture that in my head, and I say, okay, the domain is 0 to pi, range is -1 to 1, flip it all. Now I've got the inverse. That's how I think of it. Let's look at inverse regular tangent. Okay, so now we're hoping regular tangent passes the horizontal line test. Okay. What do we think? Does tangent pass the horizontal line test? Nope, that also fails it. Because regular tangent fails it, that means what? Yep.
Inverse of tangent will pass the other one, or no?
It means the inverse of tangent is not a function. Okay, if we consider that entire graph, we cannot do inverse tangent. We get infinite amount of answers. All right, so we are going to restrict what part of the graph we actually use to generate the inverse. So let's make a box. The box is always pi units wide. That's the section we always look at. Whether it's -pi over 2 to pi over 2 or 0 to pi, it's always pi units. Let's draw a box that's 2 tick marks. And if we can, we'd like to find a section that passes it and is connected. So yes, technically something like that works, but I would rather find a section that's connected. So could use that section, okay, that's in the negatives, or we can use a more common section, which is that one. So this is for original tangent. What does it look like we just restricted the domain to make it so this passes the horizontal line test? Yeah?
Negative pi over 2 to pi over 2.
Right, negative pi over 2 to pi over 2. Now, we used that number before here. Am I going to write it exactly the same way I did that one? Okay, look at the graph.
No,
No, what's different?
it's parentheses and brackets because
Right.
it never actually reaches those.
It never reaches those because what does the graph have? Does it have a hole in it? Is that why we can't reach it?
Not holes, it's
So what?
Asymptote.
Yes, we have, in the original, we have a vertical asymptote. Yep. And that prevents us from including the endpoints. What's the range of what's inside that red box? Yeah?
Oh, like with infinity to infinity.
Yeah, negative infinity to infinity. Okay, so that's regular tangent. Now, let's talk about inverse. What do you think the domain of inverse tangent is going to be? Yeah?
negative infinity to infinity.
Negative infinity to infinity, which means when you draw it, it's going to go which way forever?
Left and right.
Left and right. Okay, inverse tangent is going to go forever left and right. And what about the range of inverse tangent? Yeah?
Negative pi over 2 with parentheses still, because you can't reach it.
Right. Negative pi over 2 to pi over 2, not including it. So now there's your domain, there's your range, and we have vertical asymptotes in regular tangent. What kind of asymptotes do you think we have in inverse tangent? Yeah.
Horizontal.
Horizontal, yep, everything switches. Everything that was x becomes y, everything that was y becomes x. Okay, let's sketch that one. So there's our original, and remember, it's kind of hard to draw when it's a trig function, but if you put a black line in, y equals x, and you reflected it, this is the picture you would get. That's inverse tangent. And if I put a horizontal line in at pi over 2, and I put one in at negative pi over 2, you'll see that those two horizontal lines are going to bound that graph because they are the asymptotes. Okay, so it's always going to stay trapped in that middle section, but it is going to go left and right forever. So any question on the domains or the ranges of those three inverse trig functions? If you kind of look at it by looking at the original and then finding a section that passes, that helps it to make sense why they're picking these numbers they're picking. All right? They are not the only numbers. There are other sections you can look at. But the sections that I gave you are exactly the same sections that a calculator would use. Because that is one thing. We all have to agree on what section we're going to use. Because if we all use different sections to pass the horizontal line test, then we're all still going to get different answers. So we have to agree on everything that's up here. And that's the same way pretty much every book does it. All right, so let me go back to this. If you're going to get x by itself here, what would we have to do on both sides? Well, Jack, can you remind us how would we get x by itself there?
Inverse sign.
Can you be more specific? Give me like a full sentence of what to do.
You multiply.
No, well, you can't add, subtract, multiply, or divide to get rid of a function. Looking for a different verb besides multiply. Yeah?
You take the inverse sign of both sides.
Yeah. take the inverse sine of both sides. Okay, there's absolutely no multiplication happening there. Just like if you had this, and you did this. You didn't multiply there. You took the square root of both sides, but that is not multiplication. Same thing here. So take the inverse sine of both sides. And what happens on the left? Well, what did I tell you last week that happens on the left side? Oh, Nick.
The sine cancels out. It's just x.
The sine and the
Inverse sine.
inverse sine cancel out, and you get x. And if we try that, yes, if you take the inverse sine of the sine of 0.3, you do get 0.3. Okay, they cancel those two. I'm just showing you with a specific number that they do cancel out. In this case, I don't know what we would get exactly, but they would cancel out, and we just have to type this in on the calculator. Well, if we try something like the inverse sine of the sine of 1.5, okay, I still get back 1.5. Okay. Let's try the inverse sine of the sine of 100.8. Uh-oh, I didn't get back 100.8. I got back something different. Okay. So the fact that these two things cancel each other out, I told you that you could just cross them out, but you can't always do that. The reason we could always cross them out last week is because we were solving right triangles. So we were either solving for that angle or that angle. What do you know about this angle in a right triangle? Yep.
That angle plus the other angle always equals 90.
Always equals 90. So what do you know specifically about just that one?
It's less than 90.
It's less than 90. And anytime you are solving for an angle, and you already know the answer is going to be less than 90, that formula will work. That's why I didn't have to mention any caveat to that, because there wasn't one with a right triangle. You'd never have an angle here that got bigger than 90. Okay, that would have been impossible. All right. So let's put up that formula. I'm actually going to put it up two different ways. Let's start with that one. Inverse sine and regular sine will cancel each other out, and you will get back whatever you plug in right there, as long as x is between negative pi over 2 and pi over 2. And in a right triangle, you are guaranteed that x is always going to fall in that range. In fact, you're guaranteed x is always going to be between 0 and pi over 2. We can even be a little more specific. But is it always between negative pi over 2 and pi over 2? Yes. In a right triangle, it always would be. Okay. So let's try the same thing now, but let's do a couple in degrees. Right, let's pick an angle between negative pi over 2 and pi over 2. 47. Let's try the inverse sine of the sine of 47. When I hit enter, what should I get back? Yeah?
Hopefully 47.
Yeah, I get back 47. How come? What did I have to be between for this number for it to come back the same?
Less than 100. Not sure.
Yeah.
To be between 0 and 9 would be either.
It doesn't have to be between 0 and 90. Remember, we're not dealing specifically with a right triangle right now. So that's not between 0 and 90, but it came back the same. Yeah?
Is it negative 90 and 90?
Negative 90 and 90, what's in the box right there. Okay, so as long as you put in a number between negative 90 and 90, or negative pi over 2 and pi over 2, then those will cancel out. If you pick a number beyond negative 90 and 90, you will not get back the same answer you started with. There's a pattern to what you get back, but it's not what you started with. All right, let's try this one. It looks almost the same, but what's the difference between Formula 1A and 1B? Yeah.
In B, the inverse sign is in the parentheses, and then A is outside.
Yeah, it's an order of operations thing. Okay, which one are you doing first? Now, when you're dealing with like taking something and squaring it, and then square rooting it, that will always come out the same as that. Okay, the order doesn't matter which one you do first. In trig it does. Okay, the order is important. So for the inverse, when the inverse is on the inside, you have to be between -1 and 1. Okay, for what you plug in. So let's do the sine of the inverse sine of 0.8, and you get back what you started with. Think about the domain of that. What did we say earlier when you're doing inverse sine? What is the domain of inverse sine? If you can't remember the domain of the inverse, think of the range of the original. How high and low does the original sine go? Yeah?
Negative infinity to infinity.
No, that would be for the original tangent function is negative infinity to infinity. But sine is bounded. It doesn't go up and down forever.
Oh.
Yeah?
Negative 1 to 1.
Negative 1 to 1. So the domain of inverse sine is -1 to 1. That's why this restriction is -1 to 1. You're not allowed to fill in anything here that is not -1 to 1. If you try to, it's going to be outside the domain, and you won't even get a different answer back. You'll just get an error. You can't even do that. Okay. All right, so that's when inverse sine and regular sine cancel each other out, and you get back whatever you type in right there under those conditions. Let's do the same thing for inverse cosine and regular cosine. Okay, in general, to figure out the condition of when this formula will work, think about that. Think about the domain of regular cosine. What did we restrict the domain of regular cosine to so that it would pass the horizontal line test? Yeah? No, it wasn't -1 to 1. That's the range of regular cosine. We're looking for the domain. Yep.
0 to pi.
0 to pi. Yep. We restricted this to be between 0 and pi when we built the inverse cosine formula. If we don't stick with that restriction that we set up originally, that's not going to work. Okay. Right now, let's think about that one. The cosine of the inverse cosine, those two will cancel each other out, and you will get back whatever is circled right here, as long as what you have there is between two certain values. Think about the domain of inverse cosine. What's the domain of inverse cosine? Again, if you can't remember the domain of inverse cosine, think of the range of original cosine. Yeah? -1 to 1. Yep. And this is the same deal as the one above it. If you try to plug in a number not between -1 and 1, it won't even work in formula 2b. All right, and now let's think about the tangents. The A version of each formula, that's what you see when you're doing right triangle trig. Okay? The B version, that does not come up when you're doing right triangle trig. It might come up with other things in trig, but not when you're solving right triangles. Okay, so the inverse tangent of the regular tangent, those two things will cancel each other out. You'll get back what you started with. But what do you think x has to be between here? Think of the domain of tangent, what did we restrict the domain to? Yep. Negative pi over 2 to pi over 2. Can you just be a little more specific?
X would have to be between pi over 2.
Okay. Can you clarify what you mean by between?
X has to be negative pi over 2, but less than pi over 2.
Yes, exactly. You cannot include the endpoints. If you try to plug in pi over 2 here, you'll get an error. You can't do that because it's on an asymptote. So we have to be strictly between, not including the endpoints. And now, for the last formula, tangent and inverse tangent will cancel each other out. You'll get back whatever you typed in to start with. As long as x is between, what do you think x has to be between here? Yeah?
Negative infinity and infinity.
Yes, negative infinity to infinity. It always works. Again, to figure out the restriction, look at the inside and ask yourself, what is the domain of what's inside? The domain of what's inside is always the restriction. So you can make up anything you want. Tangent of the inverse tangent of 7.58. And you get back 7.58. Always works. All right, so any questions on those three formulas? Okay. And again, not something you had to think about when we did inverse trig, whenever you used one of those three, because you were always guaranteed to get an answer that would be in the restriction. In a right triangle, are angles always between negative 90 and 90? Yep. Are they always between 0 and 180? Yep. Are they between negative 90 and 90? Yep. So you never would get an answer in a right triangle that failed that restriction, which is why it always worked. Okay. But now you know a little bit more about it in terms of dealing with angles that might not be in a right triangle. All right. So transformations. There's nothing new to say about transformations. They work exactly the same way they do on every function we've done all year. So Dex, what's A going to do?
Horizontal shift.
Yep. And a plus would move it to the
Left
yep, and a negative.
to the right.
Perfect. Yep. So that's A. B. Well, Holly, what's B going to do?
It's a vertical, horizontal stretch.
Yep, horizontal stretch or compression. If you put in a value that's big, a value bigger than 1, what's that going to cause the graph to do?
It's gonna stretch it. I mean,
Compress. A bigger value for B causes it to compress. A small value for B causes it to stretch. And by big, I mean bigger than 1, and small means between 0 and 1. What if B is negative? Aiden. What would a negative B value do?
It would it increase it?
No, it wouldn't increase it. Let's just say like negative, specifically negative 1. Pretend B was just negative 1. I'm not sure. Michael, can you help him out?
It's a horizontal reflection.
Yep, good. That's a horizontal reflection. Or you could also say reflect over the y-axis. Okay, so that's B. C. Kaylee, what's C going to do?
it would be a vertical stretch or compression.
Yep, vertical stretch or compression. If I put a value bigger than 1 in for C, that would cause it to?
Stretch.
Yep, bigger value causes it to stretch. A small value causes it to compress. And Cecilia, if C is negative, that's going to cause my graph to?
It would be a vertical flip over the x-axis.
Yep, so that's a vertical reflection flip, and it is over the x-axis. Okay. And the last one, D. Bella, what's D going to do?
Horizontal shift.
So A was our horizontal shift, so we'll use that one.
The vertical.
Vertical. Positive would move it which way?
Up.
Up, and negative
Down.
down. Yep. All right. So again, we've written that down probably at least 5, 6 times. So hopefully by now we kind of start to know what each number is going to do. So now knowing what the horizontal and what the verticals are, what 2 letters in that formula out of the A, B, C, and D would affect the domain? Yeah?
A and B.
A and B. Anything we do with an A and a B, that is going to alter the domain. A C and a D is going to alter the range. And that's what we're kind of getting towards figuring out now. How do you find the new domain and range of an inverse trig function? Well, first of all, it requires you to know the original. If you do not know the original domain and ranges, we're not going to be able to find the new ones. Okay, so we need to know the original. And the way that we're going to find the new domain, because remember the A and the B are backwards, so we have to do this, we have to set it up like this to figure it out, is we're going to create a compound inequality. We're going to put the argument in the middle. The reason all we need to do is focus on the argument is because we're dealing with domain. C and D have nothing to do with domain. Those are vertical. A and B are the horizontal. So you're going to put whatever's in the argument in the middle of your compound inequality. Then we're going to put the original domain on the left and the right, and now we're going to have a compound inequality to solve. Okay, so here's an example of a compound inequality. Let's say we had a 2x as the argument, and just to keep the numbers simple, let's say we had something that had a domain from negative 10 to 10. Negative 10 to 10. And we had a 2x for the argument. Put the original domain on the left and the right, put the argument in the middle, and now divide everything by 2 to solve it. That would be your new domain. Because a 2, that's a big number. Big numbers cause the graph to compress. If it went from negative 10 to 10, and you compressed it by 2, it would now only go from negative 5 to 5. So you can write your answer, depending on what they ask for, either as an inequality or as an interval. I think most of the time they're going to ask for an interval. All right, so setting it up that way automatically takes into account that everything with A and B is backwards, because you have a times 2 in the inequality, but to solve it, you need to do a divide by 2 everywhere. So you have to do the opposite to solve it, so it takes care of that issue. With range, we can set it up a little differently. With range, we can more do it in a direct kind of way, because it's not backwards. All right, so first, when you're dealing with range, take into account any stretching or compressing, and then take any shifting up and down into account. So again, let me pick some easy numbers. Let's say we had a range from negative 3 to 3. And let's say I stretched my graph by a factor of 2. So let's say vertical stretch by 2. If I had a range from negative 3 to 3, and I stretched that by a factor of 2, what would be my new range? Oh, Cole, what do you think? What would be my new range?
Negative 5 to 5.
So if we go from negative 3 to 3 and we stretch that by a factor of 2.
Oh, would it be negative 6 to 6?
Negative 6 to 6. Yep, good. Okay. So we can handle that in a more direct kind of way. We stretched it by 2, we multiply by 2. We don't do the opposite. And now, let's say we took that and we did a shift up 1. If I was at negative 6 to 6 and I shifted it up 1, what would be my new range now? Yep.
Negative 5 to 7.
Yeah, we go from negative 6 to 6, negative 5 to 7. So you shifted it up 1 vertically. You can add 1 to each number in the range. So again, range you can handle in a more direct kind of way, not the opposite. All right. Let's see if we can find some new domains and ranges. Okay. So the first thing I like to do is write down if there's something that's not changing. Fill that one in first. Is there anything here that is not being changed from the original, from the regular inverse sine function? Yep.
Range.
Yeah, there's no change in the range. What is the range of inverse sine? Remember, you can't think of the range of the inverse. Think of the domain of the original. Think of the box. What did we limit it to? Yep.
Negative pi over 2, pi over 2.
Yep. Pi over 2, pi over 2. So now to find the new domain, we're going to set up a compound inequality. And by doing this, it's going to take into account that everything with domain is backwards. Okay? So we have a times 2 that's actually going to compress everything. What is my original domain for inverse sine? I need to put that on the left and the right of that inequality. Yep. Negative 1 to 1. And now, just by the rules you have to use to solve an inequality, you have to do the opposite of times 2 to solve it. So you're going to divide by 2. And what does that make my new domain as an interval? Yep. Yep, negative 1/2 to 1/2. Perfect. And that's how you find the new domain. Let's try another one. Inverse sine of 1/3 x. I'm going to do a few inverse sine ones, and then we'll switch it up with a different one. Okay, anything here that is not being changed? Maggie, anything here that's not being changed?
There's nothing in front of like the sign -1. That's not changing.
Okay, so out of those two, which one stays the same? The range, yeah. So range is going to stay the same. What is my range for inverse sine? Moises, what's my range?
Range would be negative pi over 2, pi over 2.
Yep. Negative pi over 2 to pi over 2. Okay, but my domain is changing. So we're going to set up a compound inequality. Okay. What's going to go in the middle? How about Maddie? What's going to go in the middle?
1/3 x.
Yep. We can put 1/3 x in the middle. Okay. And then on the left and on the right, what's going to go there? How about James? What's going to go on the left and the right? James, sorry.
Negative 1 to 1.
Yep, negative 1 to 1. And to solve that, we need to multiply everything by. Yep, perfect. Multiply everything by 3, and that's going to give me a new domain of negative 3 to 3. And that's exactly what should happen. A small number causes the graph to stretch 3 times as much in this case. Okay. Any question on that one? All right, let's try this one. This will be our last inverse sine, and then we'll try a couple others. Okay, what is not changing this time? Yeah, the domain. We are not changing the domain because we're doing a vertical shift. So you can keep your domain, -1 to 1. Now let's think about the range. What is the range of inverse sine? It's from what to what? Yeah.
It's from negative pi over 2 to pi over 2.
Negative pi over 2 to pi over 2. And what are we doing to the range? Or what are we doing in the whole graph?
Plus 2.
Plus 2, which does what?
Shifts it for this one up
Up
2.
2. So we're literally just going to take the range and we're going to add 2 to each number to shift it up. Because it's a fraction with pi, there's not a nice way to write it. So we're just going to say negative pi over 2. We'll do a plus 2 to it. And pi over 2, we'll do a plus 2. That's the only way to get the exact answer. Just shift it up 2. All right, let's try D, okay? Inverse cosine. All right, what is not changing this time? Yep.
Still domain.
Still domain. What's our domain for inverse cosine? Domain for inverse cosine. Yep. -1 to 1. Okay. What is our range for inverse cosine? Yep.
Normally it's 0 to pi.
Yep. But
And now we're multiplying it by 5.
stretch that 5 times as much.
So that's 0 to 5 pi.
0 to 5 pi. Perfect. Okay, that's our range. All right, and let's try one with inverse tangent. Should never have to think about that one. What's the domain of inverse tangent? Think about what it looks like. Yep. Right. Doesn't matter how you stretch, shift, compress. You can't change the domain. Range, we've got to be a little bit more careful about. What is our normal range inverse tangent? Yep.
Negative pi over 2, pi over 2.
Including or not including?
Not included.
Not including. Now that's going to be tripled. Still not including.
So negative 3 pi over 2, 3 pi over 2.
Yep. There's your range.
Sweet.
Okay, so any question on finding domain and range of an inverse trig function? All right. All right, so now they do not want the domain and range. Just list all the transformations. The way it's written doesn't quite match up with what I gave you. We would have to do a step first. What do you think we would need to do first so that this matches the format I gave you? Yeah.
Distribute the 1/4 to
Yeah.
the x plus 8.
Let's just take care of that. So now the middle looks like that. Okay, 1/4 x plus 2. Okay, so now how many transformations is it going to take to get this graph from the original inverse sine graph?
4.
4 transformations. Yep. And we do have to put them in the right order. Okay. What's the first transformation? Jack?
Shift left.
Yep, we're going to shift left 2. Okay, so we got a shift left 2. What's the next transformation? Yep.
Vertical stretch by, or vertical, horizontal stretch by 4.
Horizontal stretch by how much?
4.
Yeah, so we can say it that way. Horizontal stretch by a factor of 4. Okay, what's the third transformation? Yeah,
Vertical stretch by a factor of 1/3.
vertical stretch by how much?
Factor.
Yeah, nothing backwards with that one. Factor of 3. And the last one, the -5, is going to, yep,
Shift down 5.
shift down 5. And there's your 4 transformations. No domain and range. Okay, any question on that? All right, and the last thing, I think we kind of did this last time, just plugging in on the calculator and knowing how to get the answer. Okay. First of all, anytime you use inverse trig, think about a triangle. What would you be trying to solve for? What is inverse trig designed to help you figure out?
You're solving for the side
No, when you're using inverse trig, you're not finding a side length. Yeah, you're finding the angle. So that means when you get an answer, it could be degrees or radians. It just depends on what mode they want you to use. Okay. If you want it in degrees, inverse sine of 0.5 is 30 degrees. Even if they want it in radians, I would still do it in degrees first because I know this one's going to come out to a nice answer. If you do it in radians first and they want an exact answer, the calculator's not really going to help you. It's going to give you that 0.5235. What's 30 degrees if you write it in radians? Yeah?
Isn't it pi over 6?
It's pi over 6. The calculator won't tell you that, but that's the answer I would be asking you for. I can only ask you for an answer like that if it comes out nice in degrees. If you have something like that, it's not going to come out nice no matter which way you do it. So there's no, that same idea doesn't happen in this part. So if they want it, we'll just do it in degrees this time. You press second, inverse sine, negative 0.7, negative 44.43. And what's going to happen when you type in inverse sine of 1.2? Yeah?
It's going to give you a really messed up number. Because you're going outside the usual range.
And what's going to happen there? Yeah?
Domain error.
Right, we're going to get an error. What is the domain of inverse sine? Yep. It's negative 1 to 1. You've gone beyond the numbers you're even allowed to try to plug in, so there's no solution. That's impossible. All right, so that's 7.2, part 1. So tomorrow we'll finish up 7.2. Okay, so those are the questions on 394. Just a reminder, I'll be after school Thursday, and we have our first test on, second test for the term on Friday.